All right, again, today we're happy to have as our first speaker, Anupam Ray from the Tata Institute for Fundamental Research in India. He's a PhD student there under the supervision of Vasudev Dasgupta. He works on several aspects of dark matter, including capturing celestial objects, the possible connection to the positron excess from dark matter annihilation, and I think today's topic, which is the connection between primordial black holes and the possibility of being dark matter and the exciting opportunities in that direction. So Anupam, please, thank you for being here and please go ahead.
Yeah, thanks for having me. So today I will talk about unraveling the mystery of dark matter with black holes. This talk is based on the following works that are listed here. Oh, there is some problem. Sorry, there is some problem in screen.
You can try sharing again.
Yeah. Now it's moving. Okay. Yeah, thanks for having me. So today I will talk about unraveling the mystery of dark matter with black holes. This talk is based on the following works that are listed here. Okay, so we know that dark matter is omnipresent in our universe, but we do not know what is dark matter. So identifying the nature of the dark matter is one of the most crucial challenge in modern day science. In this talk, I will try to address this issue that black holes can unravel the mystery of dark matter. My talk is based on two topics. The first topic is primordial black hole, especially ultralight primordial black hole as a viable dark matter candidate. And the second topic is asymmetric WIMP can lead to a black hole formation, which is alternative to primordial black hole. And this scenario can be testable by gravitational wave detector. Okay, so now let me start with my first topic. So primordial black holes, many of you are aware about primordial black holes, but yeah, so these are basic slides. So primordial black holes, these are exotic compact objects. They formed in the early universe, possibly by the gravitational collapse of overdense region. So one can compute what is the density required for a primordial black hole formation. So this rho PBH, this is the required density for primordial black hole formation. It's roughly the mass of the primordial black hole divided by its volume. And if you plug numbers, then we can show that in order to produce a solar mass primordial black hole, one needs roughly a density of 10 power 18 gram per centimeter cube. And this number is used because if we compare this number with the average density of sun, which is roughly 1 gram per centimeter cube, then we can see that for a solar mass primordial black hole, the density is 18 orders of magnitude higher. And this high density can only be achieved in the very early universe, because if we write the cosmological density as a function of time, then we can show that if at time t equal to 1 second, the cosmological density is 10 power 6 gram per centimeter cube. So this high density 10 power 18 gram per centimeter cube, this is much before 1 second. So clearly primordial black hole, this large density can only be achieved in the very early universe. So primordial black holes are sirens of the early universe. Okay. So now what is the mass of the primordial black hole? The mass of the primordial black hole is also determined when they form. So this mass of the primordial black hole, which is MPBH, which is essentially C cube T by G, where C is the velocity of light in vacuum and G is the Newton's gravitational constant and T is the time of formation. This C cube T by G is essentially the mass of the horizon at that time. So if one computes that if my primordial black holes are forming at time T, what is the mass of the horizon? Note that here I am assuming that all the horizon has been collapsed to a black hole, which is certainly not correct. There is a factor which often tells us gamma, which is the order 1 factor. So this estimate is correct up to order 1 factor, because all the mass is not collapsed to a black hole. There is a certain fraction of it. But yeah, we are doing order of magnitude estimate, so maybe we can take this. Okay, so now if we plug numbers, then we can again show that if a primordial black hole is produced 10 power minus 23 seconds after Big Bang, which has a mass of 10 power 15 gram. So depending on its time of formation, primordial black hole mass can be as low as 10 power minus 38 solar mass, and it can be as high as 10 power 5 solar mass. So it's a very wide range of black holes. Also note that the primordial black hole which are produced 10 power minus 5 seconds after Big Bang. So in this mass range of 10 power minus 43, which is the Planck time, to 10 power minus 5 seconds, these primordial black holes are naturally subsolar. And we remember that there is a limit called Chandrasekhar limit. So the astrophysical black hole has a minimum mass of 1.4 solar mass black hole. So detection of a detection of a Subjunctive mass black hole is often thought as a smoking gun signature of its primordial origin. So in this talk, I will show you that the belief is not correct, but yeah, so this is one of the key motivation to people think about that. Okay, primordial black holes can easily be subsolar if they are produced before 10⁻⁵ seconds. Okay, so now I will talk about the primordial black hole as a dark matter. So historically, primordial black hole as a dark matter, this is an old idea. It's proposed by 1970s Hawking, Jeldovich. So historically, primordial black hole is one of the earliest proposed dark matter candidate, but the attention in the community has largely been increased after the detection of black hole merger by LIGO-Virgo collaboration and the subsequent proposals that these black holes may be primordial in nature. So this one of the early paper on this topic is, did LIGO detect dark matter? So the idea is LIGO has detected black hole merger. If these black holes are primordial black holes, then LIGO has already detected dark matter in the form of primordial black hole. So after the discovery of black hole merger and these following proposals, people are largely interested about primordial black hole as a dark matter. So after that, multiple techniques have been applied in order to probe primordial black hole as a dark matter candidate. So these are the exhaustive list: constraints from Hawking radiation, constraints from lensing, constraints from gravitational wave searches, constraints from dynamical effect, constraints from accretion. In this talk, I will focus on constraint from Hawking radiation because I will talk about primordial black hole in the ultralight mass range. Okay, so this is the scenario: primordial black hole as a dark matter in 2016-17. So this F is the dark matter fraction of primordial black hole. This M is the mass of the primordial black hole. F equal to 0.1 means primordial black hole can form 1% of dark matter. And you note that this plot starts from 10⁻15 gram. Why is that? Because below 10⁻15 gram, all the primordial black holes have already evaporated by now. So primordial black holes Hawking radiate and loses its mass, and one can compute what is its evaporation time scale. So all the primordial black holes whose mass is below 10⁻15 gram, their lifetime is less than the age of the universe. So now they have already evaporated, so they cannot contribute to the present day dark matter density. That's why this curve starts at 10⁻15 gram. And in this plot, you can see various colorful lines. All these colorful lines are various exclusions from by using various searches. And the belief in 2016-17 is primordial black hole is not an interesting dark matter candidate because 10⁻16 to 10⁻46 in the 30 orders of magnitude, there are at almost no window where primordial black hole can make more than 1% of dark matter. So even if it forms dark matter, it would be sub-percent level, less than 1% level. But situation has changed drastically. In recent years, multiple exclusion limits are shown to be ineffective. Many existing limits are significantly revised, and many new exclusion limits are added. So this is the current scenario of primordial black hole as dark matter. So, and the axes are similar. This PBH is the dark matter fraction of primordial black hole. This PBH is the mass of the primordial black hole, and it starts from 10⁻15 gram. And as you can see, that there is a large window from 10⁻17 gram to 10⁻23 gram, almost 6 orders of magnitude, where primordial black hole can make entirety of dark matter. So there exist no constraints in this region. Okay, so in this talk, I will try to focus on in this region, the ultralight dark matter, ultralight primordial black hole as dark matter from 10⁻15 to 10⁻17 gram, and I will also briefly talk about the asteroid mass range also. Okay, so now before going to technical detail, I will try to summarize my talk for the first part. The first point which I will talk about, the neutrino and positron emission from primordial black hole and subsequent non-detection at Super-Kamiokande and integral put stringent constraint on fraction of dark matter composed of ultralight primordial black hole. Angular momentum is a very significant quantity of black hole, and it has a significant impact on the evaporation constraint. Rotating primordial black hole as an interesting aspect to study. Primordial black hole in the asteroid mass range can be all of dark matter, as I said in my earlier slide. Observation of low energy galactic center photons by the upcoming soft gamma ray telescopes such as AMEGO can close this window by almost an order of magnitude. AGS measurement of the global 21 centimeter signal can provide an world-leading exclusion on primordial black hole in the entire ultralight mass window. So these are the papers I will going to talk about in my following slides. Okay, so since I am talking about ultralight primordial black hole, so this type of constraint, the type of constraint which I showed in this slide, so I will going to briefly talk about how does this constraint appear. Okay, so for that we need to learn a bit about Hawking radiation. So primordial black hole emit particles via Hawking radiation, and the spectrum of the emitted particle follow a black body like distribution. So this is the spectrum of the particle emitted from a primordial black hole using a Hawking radiation. So you might wondering that this process is very similar to the decaying dark matter. So forget about primordial black holes for a moment. So take as a decaying dark matter, which is emitting particle. We are trying to detect this particle in our respective telescopes and respective searches, and any non-detection would put and limit on decaying dark matter parameters. Here, decaying dark matter is primordial black hole. So primordial black hole has two parameters. One is mass and dark matter fraction. And so this is roughly the idea. Okay, so this D2 and DDT, the D2 and DDT is the spectrum of the emitted particle, and this has a black body like distribution. So this gamma, so there is a factor called gamma S. This gamma is, if the gamma is 1, then the spectrum is exactly black body. But gamma is not 1. Gamma is a complicated function, and this gamma denotes the deviation from the black body. So one needs to precisely compute the value of gamma, and therefore one can obtain what is the spectrum of the particle emitted from primordial black hole. And you can note that there is a quantity called temperature of this TPBA. This is the temperature of the primordial black hole, and you can note that there is an exponential dependence. So this means that if my energy of the emitted particle exceeds the temperature of the primordial black hole, then the emission is exponentially suppressed, and in the other end, it is power law suppressed. Maybe my next slide will be more helpful to understand this. Okay, so this is the formula for a temperature of a primordial black hole. And if we are thinking of a uncharged non-rotating primordial black hole, this temperature formula simplifies to this. So this means if a primordial black hole, which is uncharged and non-rotating, it has a mass of 10 power 13 gram, it has a temperature of 1 G. Okay, so maybe this plot will be more useful to understand. So this is the quantity I have plotted. So D2 and DDT, which is the same as in my old slide. This is the spectrum of the emitted particle as a function of the particle energy. So here I have taken a primordial black hole of mass 10 power 15 gram. So 10 power 15 gram means it has a temperature of 10 MeV. So it has a temperature of 10 MeV, and this is the spectrum for a neutrino emission. So one can analytically show that if my primordial black hole has a mass of 10 power 15 gram, it has a temperature of 10 MeV, and the emission should peak at order of 40 MeV. And as you can see, at 40 MeV, the particle peaks. After that, there is exponential cutoff, and below that there is a power law cutoff. This power law cutoff is coming from the gray body factor gamma, and this exponential factor is coming from the denominator. There is the exponential E by TPP. So this is roughly the spectrum of the emitted particle. If I change the mass from 10 power 15 to 10 power 16, the plot will shift in the left direction. So at 10 power 16 gram, the temperature is 1 MeV. So the peak will be roughly here, and then the similar behavior, the similar feature will be there. Okay, so one can compute the main message is one can compute what is the spectrum of the emitted particle. Now, using this spectrum, one can compute what is the galactic flux from primordial black hole and what is the extragalactic flux from primordial black hole. And this is very easy to compute because all these calculations are being repeated for any decaying dark matter search. So this FGAL, this is galactic flux from primordial black hole, and this FEG, this is the extragalactic flux from primordial black hole. So if I am trying to think about neutrino flux, I have to consider the contribution of galactic prime. So there are galactic primordial black holes which are Hawking radiating and emitting neutrino. We have to consider that. There are extragalactic primordial black holes which are also emitting neutrino, and these neutrinos are getting redshifted. So we have to also include that. So my total flux is galactic flux plus extragalactic flux, and this total flux has to be computed with the diffuse supernova neutrino background searches, because so this total flux has to be compared with the DSNB flux upper limit, and this will give you a conservative limit on that F versus M plane, because this FGAL, this also depends on what so it also depends on, so these things is essentially what is the number of primordial black holes. So one can, so the earlier slide which I have talked about, this is the G2 and DDT. This is emission of particle from a single primordial black hole. And this factor is essentially telling you what is the number of primordial black hole, and this number of primordial black holes involves F and M. This M is coming from the number density. So the left hand side of the thing depends on F and M, and one needs to check with this DSNB flux upper limit. So the current upper limit on the DSNB flux from Super-Kamiokande neutrino observatory, this is 2.9 μe bar per centimeter square per second in the energy range of 17.8 MeV to 91.3 MeV. And also from the Kamland experiment, this is the flux upper limit. So for Super-Kamiokande and for Kamland data, one can calculate this total flux and put this energy range. So there is a Emin and Emax. So in this energy range to this energy range, one can compute what is the total flux and compare with this. And in this energy range from this to this, one can compare with this. So we have done these two things, and we found that both the Kamland and Super-Kamiokande data exclude ultralight primordial black hole to form solitary component of dark matter. So that means that if we use these two measurements, we can show that F equal to 1 is excluded. So we can put constraint in a real constraint in the F versus M plane. However, the exclusion obtained from Super-Kamiokande is stronger in the entire mass range. So we will only quote the Super-Kamiokande result. So this is the result from our paper. So this is PBH, which is dark matter fraction of primordial black hole. This M is the mass of the primordial black hole. So this constraint, the central theme of the constraint is primordial black holes are emitting neutrinos, and these neutrinos are being searched and at the Super-Kamiokande neutrino observatory. We are not seeing this neutrino. That implies a limit on the F versus M plane. There are 4 lines in this plot. This 4 line corresponds to 4 different spin parameters. So this, if we are talking about non-rotating primordial black hole, then we should look at this line, and you can see that from 10 power 15 to 3 times 10 power 15 gram, primordial black hole cannot be all of dark matter. If primordial black hole is all of dark matter, then so Super-Kamiokande DSNB search does not allow you to do that. And also one thing to note that rotation has an interesting aspect. So if primordial black holes are rotating, then the spectrum is different. So, and therefore the galactic flux and extragalactic flux are different. And the main thing is, with the rotating black hole, you can probe more mass window. Okay. And also one thing which I forgot to tell you, that this calculation is valid for a monochromatic mass distribution. So when I did this calculation, I have to assume one mass distribution of primordial black hole. So the easiest choice is monochromatic mass distribution. That means all primordial black holes have same mass. But this is the easiest choice, but this is not a correct choice. This is not a realistic choice. So one needs to perform the similar exercise for an extended mass distribution. Let's take a log normal mass distribution and with a different width. So this mass distribution is narrower. So monochromatic is the narrowest mass distribution. This log normal has some width, and this has a more width. And clearly it matches with the expectation. As I increase my mass distribution width, the constraint flattens out and excludes more. So I can see that with a realistic extended mass distribution, say log normal mass distribution with variance 1.0, DSNB data rules out primordial black holes to form 100% of dark matter up to 10 power 17 gram. Okay. So now let me quickly summarize the neutrino derived result. Non-observation of Hawking radiated neutrino in the DSNB searches at the Super-Kamiokande excludes monochromatic non-rotating primordial black hole to form the solitary component of dark matter up to 5 times 10 power 15 gram. And if the primordial black hole is maximally rotating, then it excludes up to 10 power 16 gram. As I said earlier, that covers more mass window for primordial black hole that have rotation or which follow an extended mass distribution. One thing to note that these neutrino derived results are very robust because neutrinos are special messenger because they do not bend in the galactic magnetic field and they do not interact much. So these neutrino derived constraints are complementary to the other constraint. They are definitely robust, and with the near future loading of gadolinium in Super-Kamiokande and with Hyper-Kamiokande, this result will be improved. Okay. Now I will talk about my second topic. So maybe I should move to this slide. So yeah. So in this slide, I have promised you I will talk about this constraint. So this super K is that constraint. So this plot is for a monochromatic mass distribution non-rotating primordial black hole. So I have tried to explain this constraint. Now I will move to this constraint, the integral constraint. Okay, so here the idea is also similar. Here we will not look in the neutrino channel, we will look into the positron channel, because primordial black hole emits particle via Hawking radiation. It can emit all sorts of particles, neutrinos, photons, electron, positrons. But here in this analysis, we will look into the positron derived thing. So integral is a space-based telescope which has measured a mystery, the 511 kb gamma ray line, the flux of the 511 kb gamma ray line, and from this flux one can estimate. So you are all aware of this 511 kb gamma ray line. So 511 kb is, there is a E plus E minus annihilation and producing two photons, and this 511 kb is the mass of the electron and positron. So here the idea is, if primordial black holes are there, the primordial black holes will produce positron, low energy positron. This low energy positron will annihilate with electron and producing photon. And so this is the basic physics. So the thing is, integral has measured the flux of the 511 kb gamma ray line, and it tells us that the total positron injection rate within the galactic bulk is 10 power 50 year inverse. Now one can compute what is the positron injection rate from primordial black hole for some mass distribution, let's say monochromatic mass distribution. This gamma calculates this thing, which is the galactic positron injection rate. So this has a simple formula. So this gamma will tell you how much positron is injecting per year. So this number is has to be compared with this for a conservative limit. Why it is conservative? Because see, so for 511 kb line, the positrons are coming. So the positrons can, so if I assume that all the positrons are coming from primordial black hole, then this is the most conservative limit I can set. But this is exactly not correct. One can do an astrophysical modeling, because the positrons can come from other astrophysical sources. So in reality, what needs to be done, there are positrons from primordial black hole, there are positrons from astrophysical sources. So gamma 1 plus gamma 2, that has to be compared with this. That what does it imply? That implies a stricter constraint on gamma 1. So gamma 1 depends on it. But if for the most conservative case, if I forget about there are no astrophysical sources, then I can set the most conservative limit. And I will show you, even if in the most conservative scenario, this limit is the stringent limit in the most stringent limit in the ultralight mass window. So if you only do gamma less than 10 power 50 year inverse. Okay. So this is the result. This is the result from our paper. So PBH is the dark matter fraction of primordial black hole. PBH is the mass of the primordial black hole. And similarly, there are 4 lines for different spin parameter. If we are looking at the non-rotating case, then this is the limit. So this dashed line is the limit, and this is very special, because this limit excludes primordial black hole to form the solitary component of dark matter up to 10 power 17 gram. So yeah, so if maybe in this plot it is more visible. Yes. Yeah. So if you can see before this limit, all there are limits from Super-Kamiokande. There are limits from IGRB. The IGRB is the extragalactic background ray searches. This is the Voyager searches. So this is the limit in the previous. But in the analysis which we have done, this produced this result, which is stronger than the other three. Okay. So yes. So for a monochromatic mass distribution, this is the result. As I said earlier, monochromatic mass distribution is the easiest choice, but not a realistic choice. One needs to perform this thing for extended mass distribution. We have done this for log normal mass distribution, and you can see for a flat enough log normal mass distribution, this integral analysis rules out primordial black holes up to 10 power 19 gram, which is very nice. Yeah. But one thing to note, that unlike the neutrino constraint, this positron derived constraint has astrophysical uncertainties. So there are 2 astrophysical uncertainties to think about, to consider about. One is, unlike the neutrino derived constraint, this constraint depends on choice of dark matter density profile. Which density profile are you choosing? Are you taking an NFW profile? Are you choosing an isothermal profile? Or are you choosing something else? Also, it depends on unknown propagation distance of the emitted positron of the galactic center. So this plot summarizes the variation of the result, dark matter density distribution is taken as NFW and R max. So this unknown propagation distance. So primordial black holes are producing positron. These positrons are propagating through the intergalactic medium, interacting with electron and producing photon. So how much propagation distance I have taken. So this information is in the R max. So if my R max is 3.5 kpc and dark matter density distribution is NFW, then this is the most strongest result. And if my dark matter density distribution is isothermal and I am taking the positron propagation as 1.5 kiloparsec, then this is the weakest result. So note that depending on the astrophysical uncertainty, this limit can vary up to an order of magnitude. Okay, now I will briefly summarize the positron derived result. So precise measurement of the 511 keV gamma ray line by the space-based telescope integral provide an world-leading exclusion on ultralight primordial and black hole as dark matter. It excludes monochromatic non-rotating primordial black hole to form the whole component of dark matter up to 10^17 gram. And if the primordial black hole is maximally rotating, then it can exclude up to 6 times 10^17 gram. This constraint is stronger than the extragalactic gamma ray background constraint, which were thought to be the most stringent for almost a decade. This positron derived analysis, this analysis do strongly depend on uncertainties in the dark matter density profile as well as unknown positron propagation distance, and depending on this uncertainty, this result can weaken by up to an order of magnitude. Identification of the astrophysical sources of this low energy positron will significantly strengthen the exclusion limit. Okay, so before going to that, I want to ask, are there any questions? Should I go ahead or should I take a break?
If there's any question, please feel free to unmute. I think Irene has one. Yeah.
Yeah, I have a couple. So the first one is about the constraints that you derived by using neutrinos. And I was wondering, because you were summing the galactic and the extragalactic contribution, and you say it has to be smaller than the DSMB flux. But in principle, the galactic one contains directional information, so you can easily distinguish these. So I was wondering why you sum both of them.
Yes. So what are you saying is we can also use the spectral information? Are you
the directional information? So you can reconstruct the direction for the galactic part.
Yes,
so
yes.
There is no need to include it in principle.
So I think the answer is if we do the following analysis, then the result will be the most conservative one, right? Because so there are galactic PBHs which are emitting neutrino. There are extragalactic PBHs which are also emitting neutrino. So so in order to do an conservative analysis, we at least we need to add these two. If I throw about all this directionality information, and with this, I think what you are suggesting, with this thing, the limit can only be improved.
Yeah, exactly. That was my point, which you can get a stronger limit. Yeah, okay. And then about the 511 keV line. So I think the argument that you are applying is based on the assumption that this gamma ray line comes from a dark matter candidate, because if this is astrophysical noise or is coming from another source, then this argument doesn't apply. Is it correct?
No, so what I am saying is 511 kV gamma ray line, these gamma ray lines are coming from E plus E minus annihilation. Now the question is, who is giving this E plus? Who is giving this positron? So if I assume that all my positrons are coming from primordial black hole, then this is the limit.
Yes, but if this comes from
astrophysical sources, let's say it comes from
if it comes from the decay of some elements, or it's just a background, and so it has no real astrophysical origin, then this argument doesn't hold. So at the basis of what you are saying, you are assuming that there is E plus E minus that goes in gamma gamma. Is it correct?
Yes, I am assuming that this 511 kV gamma ray line is originating from E plus E minus annihilation. So E plus is coming to rest, and this is annihilating with electron. This I am assuming. So,
okay, yeah. Thank you.
Yeah.
Thanks.
And regarding your first question, I want to tell you a bit more about. So that after our analysis, there are some recent paper on this topic, who clearly did these papers has done the spectral analysis, but not for in the Super-Kamiokande case. They have improved our analysis using a projected neutrino mission. So Juno, Dune, and Thaya. So they have checked that what is the how does the limit changes with this projected with this proposed neutrino experiment, and obviously they found that with this projected experiments, the projected limit will be better than us. Yeah.
Maybe I'll take the opportunity to ask a couple of questions also related to the DSNB slides that you were showing.
This one?
No, the one we use some galactic and extragalactic.
This one.
That exactly. So just a couple of questions. And the first one is related to the extragalactic component. And I was wondering, isn't the rho dm, so the density of dark matter, isn't that also a function of redshift or time?
Yes. So this redshift dependence has been taken into here. So this.
Oh, I see.
So I understand your point, but yeah. So there are few steps before that. So yeah.
Okay, so it's been taken into account. Yeah. And
yes,
yes. Yeah, and my other question is, so you have, as Irene was saying, you're summing the extragalactic and the extragalactic, and yes, and you say that the sum of that cannot be greater than the DSNB, and then that means that you cannot have F PBH of 1 for some mass range. But my question is, if you have, just tell me if this argument is okay or not. Maybe it's not. If you have PBH concentration in the Milky Way, so let's say that the fraction of dark matter inside the Milky Way that is due to primordial black holes is greater than the fraction of the same fraction outside the Milky Way, wouldn't that break the limit?
Maybe I have not understood your question.
So if you have one value of the fraction inside the Milky Way, because the primordial black holes have been accumulated close to the Milky Way, inside the Milky Way, and another value of the primordial black holes outside the Milky Way, let's say, in intergalactic space, then that would mean that naturally the F galactic concentration is bigger just because you have more primordial black holes than possibly the extragalactic concentration, right?
Yes, that's absolutely correct. The limit is mostly driven by the F galactic, but the F, my point is F extragalactic needs to be added also. So although it is subdominant, but it needs to be added for completeness.
But is it subdominant because it's farther away, or
yes, because as you correctly said, it is farther away. So the rho dm has been, so this rho dm is less than this rho mw. So in the galactic case, the primordial, since primordial black dark matter candidate, we have to take one distribution, right? Suppose we take a NFW distribution. So this rho mw near Earth is 0.4 GeV per centimeter cube, whereas this rho dm is much smaller.
Okay, so there's no concentration of black holes necessarily that's different in the Milky Way than outside. It's just a matter of the rho being different. Okay, I get it.
Yes.
Okay, thanks.
I cannot see any screen.
Yeah.
So whenever you want,
then
let me know, because I cannot see the screen and also the chat box. Okay.
I don't see any more questions, so please Anupam, go ahead. Thank you.
Thank you. Okay. So yeah. So up till now, I have talked about ultralight primordial black hole as a dark matter candidate, and how to use the DSNB searches and how to use the integral searches to put stringent limit on ultralight primordial black hole as dark matter candidate. Now I will talk about a similar thing, but I think it's a bit more interesting thing, because if you remember, in my the consolidated plot, I have told you that due to in recent year, many of the exclusion limits are shown to be ineffective. If you want me why this is ineffective, I will try to tell more. But if you take my word, so in this region, that's the so-called asteroid mass region, 10 power 17 gram to 10 power 23 gram, there exists no observational constraint. So primordial black hole can make 100% of the dark matter there. So the work which I will talk about, in this work, we tried to see that can we at least project a constraint in this mass region using Hawking radiated thing. So this is the work we have done. So yeah, so yeah, yes. So AMEGO. So AMEGO is an upcoming soft gamma ray telescope, and we in this work we have showed that. So maybe I can start a bit first. So primordial black hole in the asteroid mass range 10 power 17 to 10 power 23 gram can make up the entirety of dark matter, as the exclusion limit in this mass window are now refutable. In this work, we have showed that observation of low energy galactic center photon, low energy means in the energy interval of 0.15 to 0.5 MeV, by the upcoming telescopes such as AMEGO, can close this asteroid mass window by almost an order of magnitude. It excludes monochromatic non-rotating PBHs to form the sole component of dark matter up to 7 times 10 power 17. So if you remember this plot, all this evaporation plot, this ends at 10 power 17 for a monochromatic non-rotating PBH. But with AMEGO, you can exclude 7 times 10 power 17 for monochromatic case. So you can improve. So the projected constraint is improving the current constraint in the mass range by 1 order of magnitude. Okay. So before going to technical detail, I will try to briefly summarize why we are getting this type of strong constraint. So if you remember these slides, the temperature of the primordial black hole. So for a uncharged non-rotating case, the temperature of a primordial black hole. So this mass, if the mass is 10 power 13 gram, the temperature is 1 GeV. So if I start at 10 power 17 gram, so if my primordial black hole has a mass of 10 power 17 gram, then it has a temperature of I think 10 power 4, 100 keV. I think, yeah, 100 keV. So for a primordial black hole which has a mass of 10 power 17 gram, it has a temperature of 100 keV. So, and if I go more in the direction, so from 10 power 17 to 10 power 18, the mass will be 10 keV. So the problem in the asteroid mass range is that the temperature of the primordial black hole falls in the keV region. So one should search either keV photons and keV neutrinos. So yeah, so and the problem is in the keV photon. keV photon means X-ray photon. So there are many existing X-ray telescopes like links, not links. There are like Chandra, New Star. So one should ideally search for this signature. So primordial black holes are emitting X-ray photon, and we are trying to primordial black holes are emitting X-ray photons via evaporation, and we are trying to see this X-ray photon with New Star, Chandra, this type of X-ray telescope. But we tried to do this analysis, but the problem is in that analysis we find that the bound which is obtainable from this analysis always greater than 1. That means it is not probing any new parameter space. That's why we went to the upcoming X-ray telescope, which has a much better resolution and much larger effective area. Okay. So the calculation is very similar to the earlier calculation. So one needs to calculate. So since it's photon, one also needs to take care of the galactic flux, and one needs to take care of the extragalactic flux. So this is the galactic contribution. This is the extragalactic contribution, and also there are galactic astrophysical background. There are extragalactic astrophysical background. So this is this 5 gal VKG. This is the galactic astrophysical background. This is the extragalactic astrophysical background. So now here we are setting a projected exclusion. So we need to do a better statistics here. So this is the galactic background parameters. There are 4 galactic background parameters. There are 2 extragalactic background parameters. So in total, there are 6 background parameters, and there is only 1 signal parameter, which is F. So for a given mass, we can compute the spectrum, and it only depends on F. So in total, there are 7 parameters, and then with these 7 parameters, one can apply in Fisher forecasting and to compute this limit. So these two are the limits obtainable from the AMEGO. So this F is the dark matter fraction of primordial black hole. This M is the mass of the primordial black hole, and all these colorful lines, these are the colorful lines which I have showed in my earlier slides. And this constraint, this is the constraint if AMEGO. So primordial black holes are emitting soft X-ray photon, keV photon, and keV MEV photons, so 0.15 to 5 MEV photons, and we are trying to see these photons with the upcoming X-ray telescope. And if we do not see any, then it will project an exclusion. So with 1 year, with 1 year of observation, and for a monochromatic mass distribution, AMEGO will rule out primordial black hole up to very close to 10 power 18 gram, and that's good, because from 10 power 17 to 10 power 23 gram there are no observational constraint. And with rotating primordial black hole, this constraint extend more, and as expected, with from monochromatic to an extended mass distribution, this constraint will extend more. Okay, so and the next thing I will try to talk about before finishing the primordial black hole section, this is constraint from edges. So edges experiment to detect the global epoch of reionization signature. So edges has a measurement of a global 21 centimeter signal. So this measurement can be used to set a world leading expression on fraction of primordial ultralight primordial black hole as dark matter. So note that. So the previous things which I have talked about, the DSNB thing, the integral thing, and the AMEGO thing, these are sensitive to one channel. So for example, in the DSNB case, we are taking the primordial black holes and emitting neutrinos, and we are only looking at the neutrino channel. In this process, we are throwing out information of the other. For example, in the integral case, we are looking at only the positron channel. For the AMEGO case, we are looking at the photon channel. But in this probe, we are looking at all channels. So here the idea is very simple. The primordial black holes are emitting all sorts of particles depending on its mass. So these particles are propagating through the intergalactic medium, and what is happening, that they are producing an extra heat, and they are producing an extra ionization, and as a result, so maybe I should start from okay, maybe I should start from this side. So primordial black holes are Hawking radiating and producing particles. These particles are propagating through the intergalactic medium, and as a result, they are providing an additional heating and additional ionization, and this damps the amplitude of the global 21 centimeter signal. So one can compute what is, so this QC, this QC is the so this QC is the power density to a particular channel C. So C can be heating and C can be ionization. So if primordial black holes are there, one can compute what is the additional heating to the intergalactic medium, and also one can compute what is the additional ionization to the intergalactic medium. So there is the expression for delta TB. So delta TB is the global 21 centimeter signal. So this is a plot of global 21 centimeter signal. So this is the edges measurement, and this delta TB, there is a term called TS. The TS is the spin temperature, and this TS will be affected by QC. So if primordial black holes are there, primordial black holes are emitting particles. As a result, these particles are interacting with the IgM, provides an additional heating and additional ionization. This is encoded in the QC. This QC will change this TS, and as a result, this will change. And this is the best fit that we have obtained for a given primordial black hole mass. So suppose we take a primordial black hole mass of 10 power 15 gram, non-spinning and uncharged, with the other astrophysical parameter. So the thing is, we can obtain a best fit. Maybe I should move ahead to this plot. Okay, so this is the similar constraint. This is APBH, the dark matter fraction of primordial black hole. This MPBH is the mass of the primordial black hole. These are all these lines are the existing exclusion limit, and this is the exclusion limit that we have obtained from the edges 21 centimeter. Okay, so maybe I should finish this thing. So now I would like to conclude in the first part of my talk. Primordial black hole as a dominant component of dark matter had been written off a few years ago. However, such a conclusion is premature. Primordial black hole can make a large or even entire fraction of the present day dark matter density over a wide mass range. Ultralight primordial black holes emit particles via Hawking radiation, act as a decaying dark matter, and can be probed via searching this Hawking emitted particle in various space as well as ground-based detectors. DSNB searches at the existing neutrino detector, measurement of the 511 keV gamma ray line, and observation of the galactic center photon by the eminent telescope, and also the 21 centimeter cosmology provide world-leading exclusion on ultralight primordial black hole as dark matter. Still, there is a wide mass window remains which needs to be explored, and many more ideas to come. Okay, so maybe so maybe I am running out of time. So now I will move to my second part. So far I have talked about that ultralight primordial black hole as a viable dark matter candidate, and there exist various probes which can test this scenario. Now I will talk about something different, which I am currently working on now. So this thing is, so here we are not talking about primordial black hole. Here we are talking about particle dark matter accretion in compact stellar object. Okay, so here we will talk about particle dark matter accretion in compact stellar object. But the so maybe I should tell you the story first, and then I will go into detail. So if there is there is particle dark matter. Suppose they are non-annihilating in nature, and they have a non-zero interaction strength with stellar nuclei. Then what would happen? This particle dark matter will accumulate inside inside a stellar object. And since the particle dark matters are non-annihilating in nature, what would happen? This particle dark matter will accumulate inside the stellar core, and since they are non-annihilating, so with time the accumulation will be more and more. And after some point, if the number of captured dark matter particle exceeds the black hole formation condition, then a micro black hole will form, and this micro black hole will eventually eat up the star, and as a result, there will be a black hole, which we call it as a transmuted black hole. So maybe I can start from this side. Okay. So recently, LIGO-Virgo collaboration has detected unusually low mass compact object. For example, GW190814, GW190425. So LIGO-Virgo collaboration has detected unusually low mass compact object, and we do not know what is the origin of this low mass black hole. This low mass black hole can be stellar, and these low mass black holes can be primordial. But the situation will be interesting with the detection of a Subchandrasekhar mass black hole, because Subchandrasekhar mass black hole is usually thought as a smoking gun signature of its primordial origin. So all the black holes they have detected, they are not clearly Subchandrasekhar, but detection of a Subchandrasekhar mass black hole will point to the fact that we have detected a Subchandrasekhar, we have detected a primordial black hole. In this talk, I will show you that detection of a Subchandrasekhar mass black hole is not a smoking gun signature of its primordial origin. Non-annihilating dark matter with non-zero interaction strength with stellar nuclei is sufficient to produce Subchandrasekhar mass black hole. And therefore, the vital question comes: if I detect a low mass black hole, suppose we have detected a Subchandrasekhar mass black hole, how do we know that whether this black hole is stellar black hole, or whether this black hole have a stellar origin, and whether these black holes have a primordial origin? I will show you that the cosmic evolution of the binary merger rate, especially measurement of the binary merger rate at higher redshift, can conclusively determine the origin. Okay. So before going to that, let me take a step back and briefly again tell you that what formation mechanism of low mass transmuted black holes. Okay, so this is a pictorial representation of dark matter accretion in stellar object. So this is a stellar object, and these pink dots are the stellar nuclei. These blue dots are this blue dot is the dark matter particle. So dark matter particle from the galactic halo owing to their interaction strength with stellar nuclei. So dark matter particle from the galactic halo owing to their interaction strength with stellar nuclei interacts. As a result, so suppose dark matter particle is coming with a velocity. This velocity will be increased when they will approach the star, and after it hits with the stellar nuclei, its velocity will be decreased. And if the final velocity of the dark matter particle after scattering falls below the escape velocity, then it will form a bound orbit, and it will consider to be as a captured. So dark matter particles are coming, they're hitting with the stellar nuclei. We have to check that whether their final velocity is less than the escape velocity or not. If the final velocity falls below the escape velocity, then the dark matter particle will form a bound orbit. It will rescatters and eventually sets into the stellar core. and it will be considered as a captured. So now the thing is, if the dark matter particles are non-annihilating in nature, then with time there will be more and more number of captured dark matter particles. And now if the number of captured dark matter particle exceeds some black hole formation criteria, then what will happen? A micro black hole will form at the core. And now the micro black hole will start to eat up the star. And if we can show that there is some parameter space for which the micro black hole will, so micro black hole will eat up the star, and therefore the resultant mass of the black hole will be the mass of the stellar object. And if I am talking about a 1 solar mass neutron star and 1 solar mass white dwarf, then the final mass will be 1 solar mass black hole. In that process, we can generate a we can generate a subjunctive mass black hole, or say subsolar mass black hole. Okay, so this is the alternative. So initially the thinking is, if I detect a subjunctive mass black hole, let's say 1 solar mass black hole, then probably people think that okay, we have detected a primordial black hole, but this is not correct. There exists viable alternative scenario, which is very simple, that particle dark matter with which is non-annihilating and which has a non-zero interaction strength with stellar nuclei is sufficient. Okay, so now one actually needs to compute that one actually needs to check that the story which I have told you is valid or not. So first one needs to compute what is the capture rate of this incoming dark matter particle. This capture rate obviously depends on incoming dark matter flux, number of target, scattering cross section, and the capture probability. This capture probability is nothing but that if the dark matter particles is scattering with the stellar nuclei, are we satisfying that the final velocity of the dark matter particle is less than the escape velocity or not? So this probability, this is encoded in the capture probability. But one thing to note that this capture rate, the formula which I have written, this assumes single scattering between dark matter and the stellar target. What do I mean by that? The dark matter particles are coming, hitting the stellar target. After one collision, we are deciding that if its escape velocity is reaching below its final velocity is reaching below escape velocity or not. So if after one scattering, its final velocity becomes less than escape velocity, then we will consider it as a captured, else not. But this is actually not correct, because it can so happen after first scattering its velocity not less than escape velocity, but after second scattering it does. So actually one needs to calculate this in a multiple scattering approach. But the compact object, the mass of the dark matter and the cross section of the dark matter which we are working on, we have explicitly checked that if we incorporate the effect of multiple scattering, the answer remains more or less same. It changes the answer by 10%. Okay. So after one computes the capture rate, one can compute what is the total number of captured dark matter particles. So this total number of captured dark matter particles, this is very easy. This is capture rate times age of the stellar object. So this T age times C, this gives you the total number of captured dark matter particles. And as I told you earlier, this capture rate formula obviously depends on dark matter mass and dark matter nuclear interaction strength. So the left hand side is a function of dark matter mass and dark matter nuclear interaction strength. And this total number of captured dark matter particle has to be compared with the number of particles required for black hole formation. So this number of particles required for black hole formation, this is essentially comparison between two terms, n phi self and n phi Chandrasekhar. This n phi self is the number of particles required for self gravitation. So that means that if my captured dark matter particle reaches this n phi self, then the so dark matter particles are getting captured. They are thermalizing in the stellar core, and if this number reaches n phi self, then the collapse starts. And this n phi Chandrasekhar, this is the Chandrasekhar limit. So this physically tells you if my collapse starts, how long the collapse is sustainable. That means if my dark matter particle reaches this n phi Chandrasekhar, then the collapse is not sustainable and it will form a black hole. So therefore, this total number of captured dark matter particle has to be compared against maximum of these. So n phi self will tell you that the collapse has been started, the self-gravitating collapse has been started or not, and n phi Chandrasekhar will tell you this collapse is sustainable or not. Note that this n phi Chandrasekhar depends on dark matter spin, whether dark matter is boson and fermion. This n phi self does not depend on dark matter is boson and fermion. Therefore, this inequality has an intrinsic spin dependence. So for bosonic dark matter and for fermionic dark matter, the parameter space will be different. Now, this is the plot which I want to talk about a bit. So this y-axis is sigma chi n. This is dark matter nuclear interaction strength. this which is in centimeter square, this m chi, this is mass of the dark matter, which is in GeV. For the left panel, we have assumed a bosonic dark matter. For the right panel, we have assumed a fermionic dark matter. This gray shaded region, this Panda X and Xenon 1T, these are the exclusion from underground direct detection experiment. This region, this excluded from existence of a PSR J043174715. This is an astrophysical exclusion obtainable from an existence of a pulsar. And this red shaded region, is the parameter space required for transmutation. So what do I mean by that? So for example, if I am talking about a 1 point, so also to note that in this, while deriving this plot, we have taken a 1.3 solar mass neutron star. So to read this plot, this is follows. Suppose I take a 1.3 solar mass neutron star, and this 1.3 solar mass neutron star is residing in a region where the dark matter density is 10 cube GeV per centimeter cube. Then if my dark matter mass is 10 power 5 GeV and my cross section is 10 power minus 47 centimeter square, then the transmutation happen and a black hole will form. So for a 1.3 solar mass neutron star will be converted to 1.3 solar mass black hole if my dark matter mass is 10 power 5 and cross section is 10 power minus 47, and it is residing in a region of 10 power 3 GeV per centimeter cube. Let's say it is residing near Galactic Center. Similarly, suppose I have taken a 1.3 solar mass neutron star. It is residing in a region of 1 GeV per centimeter cube, and if my mass is 10 power 5 and cross section is 10 power minus 46, then the transmutation is occurring. So this is so all this red shaded region, which is not covered by this gray shaded region, this is the required parameter space for transmuted black hole formation. If you are seeing my cursor, so for a dark matter density of 1 GeV per centimeter cube, this small strip will occur a successful transmutation, and for a dark matter density of 10 cube GeV per centimeter cube, this small strip, this large strip will occur a successful transmutation. This is for a bosonic dark matter. The right side plot is for a fermionic dark matter. Okay, so the main takeaway from this plot is for a reasonable value of mass, for a reasonable value of dark matter mass, and for a reasonable value of dark matter nucleon cross section, transmutation occurs. Okay, so now the vital question comes that, okay, so if I have, so already LIGO Virgo has observed some unusually low mass compact object. If these unusually low mass compact objects are black hole, then we need to understand that whether these black holes are stellar black hole or whether these black holes are primordial black hole. So since it's a very elegant scenario, we need to consider that. So now the question is, with the detection of a low mass black hole or with the detection of a sub-Chandrasekhar mass black hole, how do we know that these black holes are stellar origin or these black holes are primordial origin? In that work, we have discussed about few possibilities listed here to identify the origin of the black hole, but due to the lack of time, I will probably talk about the first part, cosmic evolution of the binary merger rate. This can help us to understand whether these black holes are primordial black hole or whether these black holes are stellar black holes. Okay, so cosmic evolution of the binary merger rate can be used as a probe to determine the origin of a low mass black hole. So if you concentrate on this plot, this y-axis, this is merger rate in the units of gigaparsec cube per year, and this is the redshift. So this is merger rate as a function of redshift. So this red line is the neutron star merger rate. So binary neutron star merger rate normalized to the latest LIGO Virgo measurement. These two blue lines are the transmuted black hole merger rate. So for this, so since we are talking of, so there is a neutron star. So there are neutron stars which are being transmuted for some dark matter mass and some dark matter parameter. So for this blue line, dark matter mass is assumed as a 10 power 4 GeV and the cross section is assumed as a 10 power minus 45 centimeters square. Note that this combination is not ruled out by any. This combination is not ruled out by any exclusion. So for a dark matter mass of 1 TeV and cross section of 10 power minus 45 centimeters square, we obtain this is the merger rate, and for dark matter mass of 1 TeV and dark matter cross section of 10 power minus 47 centimeters square, we obtain this is the merger rate. And this blue line is the primordial black hole merger rate. But interestingly, you note that this two curves has a distinctly different behavior. This transmuted black hole merger rate, this peaks at order 1 redshift and this falls off, and it's very expected because these transmuted black holes are coming from the dark matter assisted collapse of neutron star, and this neutron star has this this will follow the cosmic star formation history because this has a stellar origin. So this is coming from a stellar collapse. So definitely it has a connection with the cosmic star formation rate. And as we know that the cosmic star formation rate peaks at order 1 redshift, and after that it falls off. And therefore this signature is also reflected in the TBH merger calculation. And also to note that if we can see if my cross section is being smaller, then I am getting a low TBH merger rate. This is also expected because low cross section means there is a low rate of transmutation, because as the cross section is higher, the number of captured dark matter particles is also higher, because the number of captured dark matter particle is proportional to the cross section. And therefore if I decrease if the cross section is decreased, this implies the low number of dark matter captured, low number of captured dark matter particles, and therefore less chance of transmutation. And that also tells you that why the merger rate is going down if I reduce my cross section to 2 orders of magnitude. On the other hand, the primordial black hole merger rate has a completely different characteristics, because primordial black hole merger rate does not follow cosmic star formation history, as I have showed you, as I have tried to show you in my earlier talk. So these primordial black holes are formed in the very early universe. So with redshift, it is expected that they will, with high redshift, it is expected that they merge more efficiently, and therefore leads to a larger merger rate. So this transmuted black hole merger and this primordial black hole merger has a completely distinct redshift dependence. And fortunately, with the upcoming gravitational wave experiment like pre-Desigo and Einstein telescope, we will be able to measure merger rate as higher redshift. So currently with LIGO, we are measuring around 0, around redshift 0. But with the 3rd generation gravitational wave experiment, we will measure redshift up to 10 and even beyond more than 10. And therefore, we can clearly distinguish what is the origin of what is the origin of a Subjunctive mass black hole. So if we see a low mass black hole with the upcoming gravitational wave experiment, we will be able to tell that, okay, these black holes are of primordial origin, or these black holes are from transmuted origin. Okay, so now I would also like to conclude this section, and I would like to finish my talk that Subjunctive mass black hole, probably I have able to convince you that Subjunctive mass black hole is not a smoking gun signature of its primordial origin. Non-annihilating dark matter with non-zero interaction strength with stellar nuclei is sufficient to produce a Subjunctive mass black hole of non-primordial origin. With remarkable advances in gravitational astronomy, we have already started to observe unusually low mass black holes. Measurement of the binary merger rate, especially at high redshift, by the upcoming gravitational wave experiment will definitely settle their origin, and therefore can test the particle dark matter hypothesis. Thank you.
Thank you very much, Anupam. It was very comprehensive. So thank you for that. Do we have questions from the audience?
Yeah.
Maybe I'll start with one. We can maybe have 2 or 3. My question is, am I correct in understanding that if you're so no, what I should ask is the following: how uncertain are the values of the masses and the cross sections in one of your final plots? Maybe you can show it. It would be easier to explain it there.
Sorry, maybe I should.
I think it's the next to, the next to last. Yeah, that one. So what I'm trying to figure out here is how well can you actually put a limit on the PBH merger versus TBH merger given an observation? What I mean by that is, once you trace over sigma, once you trace over m chi, how much does that affect your results?
I see. I understand your point. So you are saying all these lines have a band, right? That
exactly.
So I should have told you because of the lack of timing. Yeah. So exactly, you are right. So this neutron star merger rate, this too has a band. So this line I have quoted, this is the median value. So LIGO measurement of the binary neutron star tells you that the binary neutron star at redshift equal to 0 has to be 320 plus minus something. I forgot the error bar. So indeed, there is a band associated with this neutron star merger, and therefore this TBH merger calculation is essentially coming from the neutron star merger, because these TBHs are nothing but dark matter assisted collapse. So therefore, it has also a band. So and I think the primordial black hole merger has also a band. So now one needs to check with this band. Maybe it will be more difficult to tell, but as you can see, that even with the band, the line pattern will be same, right? So suppose there is a band in the TBH merger, but the main feature that the TBH merger will peak at order 1 redshift and then it falls off. On the other hand, the primordial black hole merger, it will keeps rising. This message will be same even if I add the band, right? And so suppose I measure a redshift equal to 10, then I think we can clearly tell that whether these black holes are primordial origin or whether these black holes are transmuted origin. Does that answer your question? I'm not sure whether
no, if you tell me that the bands are small enough, then that's fine.
Yes.
Do we have
the bands are not very big enough, but in this plot I should have plotted the band, but here I have plotted only the median value.
It's perfectly fine. Thank you. I think Rasmus has a question. Rasmus, do you have a question? Your hand is up. Rasmus, your hand is raised, but you're muted. If you're speaking, you have problems with your microphone. Okay. Maybe in the meantime, let me ask you one thing while Rasmus solves this. So for the what's it called, the transmutation, you need your dark matter to be Majorana, right? Sorry, to be not Majorana, to be direct.
Sorry, can you repeat it?
For your TBH cases, for your transmutated black holes, you're assuming that you're accumulating dark matter, and they are not self-annihilating.
They are not self-annihilating. Yes, so that means that it has to be direct.
So it has to be direct. Is there any possibility of doing it with Majorana? Say if they are puffy, so if they're not exactly in the same spot, so that their self-annihilation rate is damped somewhat.
Yeah,
have you thought about that?
That's a very interesting question. So I do not know the answer, but what do I know? So if the as you correctly said, if the cross section is not, if the annihilation cross section is not damped, suppose I am taking a Majorana dark matter with a thermal relic cross section, then I think you cannot form a black hole. So if you somehow reduce this annihilation cross section, I think you have to decrease it a much lower amount, and I think it's hard. So as I remember, if the annihilation cross section is less than 10 power minus 40 centimeter cube per second, then probably with Majorana you can form this type of black hole.
I see. Okay, so it might be possible.
Very low number. Yes,
but it's difficult.
Yes, and also, with respect to the fermionic case, in the bosonic case, it's easier. So because as I tried to tell you that this Chandrasekhar limit is different for bosonic dark matter particle and fermionic dark matter particle. This difference is essentially coming for fermionic dark matter particle. This has to be deal with the Pauli exclusion principle. For bosonic dark matter, there are no Pauli exclusion principle. So bosonic dark matter collapses easily. So, and this is also reflected here. So for a 10 power 4 GeV and 10 power minus 45, you are getting a black hole formation criteria. But here you have to talk about a very large mass. And also, if you note that these masses are really weird and large. This 10 power 7 GeV. This yeah.
Okay, so thanks. I'll ask Rasmus's question, and it will be the last one. I will read it to you. Is the fit for edges that you showed did not look like a very good fit. Maybe you want to go there. Yeah. How robust can the conclusions then be?
How robust can be?
Can the conclusions based on this be?
Yeah, it's an interesting question. Yes, yes, I agree with this point. This fit is not, yeah, the if we look at the chi-square per degrees of freedom, it's clearly less than, it's not less than 1. Yeah.
Yeah.
Yeah, yeah, maybe I don't want to, maybe I should not tell if I'm not sure about this.
Okay, that's fair. All right.
I will try to think about this, and I will let you know if there is some answer to it.
Thank you. I don't see any more questions or raised hands. I guess Rasmus, that's your old hand probably. So I'll assume it is. Or Rasmus, are you going to say something now?
No.
Okay. No. Thank you. All right, Anupam, thank you so much. This was very interesting. Thank you for giving us your time. And congratulations on a.
Oh yeah, I'm being late because I took more than 1 hour.
That's perfectly fine. Congratulations on a good piece of work.
Okay.
Thanks everybody for being here, and we'll see each other in a couple of weeks for the next seminar. All right, thanks, Anupam.
Okay, thank you.
Thank you.
Thank you.
Bye-bye.
Bye.
Bye.